Hello good people, we have another problem in front of us. This time we need to calculate the cell potential under non-standard conditions. So we are given the Nernst equation on the right, which will come in useful later on, and we are given the two half-cell equations on the left. Seeing how this is a redox question, it's always a good idea to figure out which one of these two half-cells is your cathode and which one is the anode. Well, we know that the more positive the standard reduction potential is, the greater the chance that that half reaction will undergo reduction. In this case, it is the copper half reaction that has the more positive standard reduction potential. So I can write that this half cell, or this half reaction, will be the cathode, which means the other one is the anode. Another thing that I like to write is that reduction will occur at the cathode, and oxidation will occur at the anode. It's just something to keep in mind because it might become important later on. Next thing to do, seeing how this is chemistry, is to have a balanced chemical equation. So we need to combine these two half reactions. So the copper half reaction, we have already said, will undergo reduction, which means we can use it as it is written, because it is already written in its reduction direction. The iron half cell up here is written in the reduction direction. However, we have said that it will actually undergo oxidation. That means we need to flip it around. So we'll have iron solid go to iron 2 plus, aqueous, do not forget the states, plus 2 electrons. The half reactions are balanced, the charges are balanced, there are equal number of electrons in both of the half reactions, which means we can add them. And we can also see that the electrons will cancel. So that will leave us with copper 2 plus and iron solid on the reactant side, and copper solid and iron 2 plus on the product side. All right. What is the next thing we can do? Well, an easy thing that we can do is calculate the cell potential under standard conditions. How do we do that? Well, E naught cell equals the standard reduction potential of the cathode minus the standard reduction potential of the anode. In our case, that is plus 0.34 minus negative 0.44. Minus and a minus give a plus, which means the standard cell potential is 0.78 volts. All right. However, we need to calculate the cell potential under the non-standard conditions given up here in the question. So now let's have a look at the Nernst equation and what all of these letters mean. Well, E naught, that is our E naught cell, and we have just calculated that. So I can write that E naught equals 0.78 volts. R is the ideal gas constant, 8.314, pardon me, joules per mole Kelvin. Temperature, well, it is given as 50 degrees Celsius, but we need it in Kelvin. So that means 50 plus 273, that should be 323 Kelvin. Next we have N. N is the number of moles of electrons involved in the process, and we have figured that out to be 2. So we can write 2 moles of electrons. F is the Faraday's constant, 96,485 joules per volt per mole of electron. And then we are left with this tricky Q. What is Q? Q is the reaction quotient. Reaction quotient. What is that? Well, this goes back to our equilibrium. And all it is concentration of products raised to the power of the molar coefficient of products over concentration of reactants raised to the power of the molar coefficient of the reactants. What is that in our case? Well, what do we have on product side? On the product side, we have copper solid, and we have, not copper 2+, pardon me, we have iron 2+, aqueous. On the reactant side, there is copper 2+ aqueous and iron solid. In terms of numbers, well, the concentration of a solid is taken as 1, so we can just write for copper solid 1. The concentration of iron ions is given up here as 0.24. 0.24. The concentration of copper ions is given also in the question as 0.72. 0.72. And the concentration of iron solid can be taken as 1. That leaves us with 0.24 over 0.72, which is 1/3 or 0.33 recurring. All right, so now we have all of the things that we need for our Nernst equation, and it's just a matter of plugging in those values, and I'll do it now here on the left-hand side. So we have 0.78 for the standard cell potential minus R, which is 8 point, actually let's do that in red to make it a little bit clearer. So 8.314 multiplied by the temperature, which we have said is 323. Oops. Over 2 moles of electrons times the Faraday's constant. And I suppose I should make this orange, so 0.78. ln of Q, which we have calculated to be 0.33. So now it is a matter of plugging in those numbers into a calculator, and I shall do that here quickly on the side. 8.314 times 323 divided by 2 divided by 96,485, and I get 0.014 with rounding. And then we need to take the natural log of 1/3, which is negative 1.1. All right, almost there. So now we have 0.78 minus 0.014 multiplied by 1.1, pardon me, negative 1.1, and that gives us negative 0.016 with rounding. Almost there. So that means we have 0.78 minus and a minus, minus and a minus make a plus, 0.016. And finally, we can say that the cell potential under these particular conditions is 0.796 volts. That is all for now, and I will see you on the flip side.